back to fitting our binomial model. Now, we have at this point a model with two constraints. We have the logistic regression form. We have examples of how we can convert sort of satisfaction violation profiles into these numeric codings. And our goal now is going to be to estimate good values for the model parameters. That is the strength or the weight of the short before long constraint and the strength or the weight of the frequent before infrequent constraint. And we're going to do that from data. And in order to do that, I want to remind you that we need two things. We need data and a method of fitting. So for data, we would go out and collect a set of these binomials from naturalistic text. So we'd get more and more examples like the ones below. Actually, a much larger data set is what I'm going to show you the results from. And then we have to choose a fitting method. So for example, we might choose the method of maximum likelihood estimation, where we find beta hat syllable and beta hat frequency. Hat is for the best single point estimate. In this case, the maximum likelihood estimate. So as you may remember from earlier in the semester, when we're doing estimation like this, we need to think about the surface of the likelihood. So the likelihood is a function of the model parameters when the model is evaluated on the data that we have, and the likelihood is the probability that the data defines, the probability that the model gives to the data is a function of the choice of our model parameters. And I've given you here a contour plot, and this is what's called a convex surface. So the surface has only one maximum. It's sort of obvious what it is. And logistic regression is very well behaved this way. The logistic regression likelihood surface is convex. That makes it relatively easy to find the optimum. In practice, for a wide variety of fitting techniques, there's a crucial notion that we're going to have, which is the gradient, which you can think of as the derivative in all directions on a multidimensional surface. So the gradient, in this case, visually is the direction, the vector of the maximum increase in likelihood as you move locally on the surface. And we denote it with this upside down triangle. This is the gradient as a function of the model parameters beta of the likelihood of the data with respect to the model parameters. And in this case, it has this form because there are two model parameters beta, so there's two parts to the gradient. And it turns out in this case, that maximum likelihood estimate is the values 0.48 and 0.4. So that is the maximum likelihood estimation. We're going to go on now to looking at the properties of that maximum likelihood estimate. So, and in particular, I want to draw your attention to an interesting fact, which is that if you think about the question of what parts of the space of predictors X, of predictor values X, does logistic regression predict that quote unquote success, whatever you defined it as, is a probability higher than 0.5 versus lower than 0.5, logistic regression determines a hyperplane boundary between those two regions. To help you understand this, let's look again for this example for the 0.48, 0.4 values of syllable and frequency. Notice that this says that basically short before long matters a little bit more than frequent before infrequent. We have our fitted model parameters plugged into our linear predictor, and then we have the link between the linear predictor and the probability of success. And notice that this probability of success will be, if this is 50-50, then that would be the hyperplane boundary between where we predict success is more likely versus failure is more likely. And to think about that, in turn, let's look at the relationship between the linear predictor eta and the predicted mean rate of success mu. And you'll notice that mu is predicted to be 0.5 when eta is 0. So that means when eta is 0, we're on the hyperplane boundary. So if we think about that with respect to our linear predictor equation, then we have 0 equals 0.48 times x of syllable plus 0.4 times x of frequency. At that, when those two when values of x have that property, then we're on the hyperplane boundary. Solving for this, we get that x of frequency should be negative 0.48 over 0.4 of x of syllable. And we can visualize this actually in the following way. So if we plot our examples, here are 4 examples that I plotted. Because the two x predictors are given values only 0, 1, and -1 in this case, it's sort of a discrete space, but you could imagine that we might use continuous versions of these predictors instead. For example, we could use the difference in the log frequencies between the words as a continuous predictor for the frequency dimension, or maybe the difference in number of syllables as some kind of more continuous numeric predictor for the syllable dimension. And this line is the hyperplane separator between the region in which the model predicts that the order that you're considering is more likely than the reverse order, and versus the region where the order that you're considering is less likely. And this corresponds to the fitted model intuitively, calm, relaxed, and relaxed satisfies both constraints. Crochet and knit satisfies neither constraint. Carefully and calmly, cruel and unusual each satisfy one constraint. The word length constraint is a little stronger. So the one that satisfies the word length constraint and violates the frequency constraint is predicted to be more likely than chance, and the one that satisfies the frequency constraint and violates the word length constraint is predicted to be a little less likely than chance. Now, that's great, but actually this mechanism that logistic regression offers is really not a fully general mechanism that we're going to want for solving all sorts of learning problems. And the reason is there are lots of interesting problems that aren't linearly separable. Perhaps the most famous one is the exclusive OR problem. So exclusive OR is very simple. Here we have, as a function of two binary variables, an outcome class prediction. And of course, for exclusive OR, we have one class, we'll call it class 0, the success class, where only one of x1 or x2 is equal to 1, and in that case, we're in class 0. Otherwise, we're in class 1. And we can visualize this in the following way. So it's sort of immediately obvious once we visualize it that there's no way to draw a linear, draw a hyperplane in this space that would separate the red dots from the blue dots. And more generally, this is a simple example, but more generally, we want models that can build and learn flexibly shaped class boundaries. This is an important part of pattern recognition for intelligent agents. And so how are we going to do that? So in this point, we're going to turn to inspiration of thinking about logistic regression as a kind of sort of modeling of modeling of a super simplified version of a single neuron. And if you think about the structure of a neuron, it gets input, feed-forward input. There's context that's coming in from other neurons that is modulating the way that input is treated, and then it sends out some output. And we're going to think about the behavior of our logistic regression system as the way that input and context modulate the output behavior of a neuron. And this, of course, is a dramatic oversimplification with respect to biology, but it's been crucial in the development of theoretical neuroscience and computational approaches to neuroscience and AI. And so the idea here is that the inputs are individually aggregated. There's sort of a default rate, we'll call the bias, at which maybe the rest of the neurons rest on resting state. These inputs are aggregated with some kind of weighted sum, and then they're transformed through some nonlinear activation function, like the sigmoid activation function, that gives it an output. And that's the output is what the neuron sends to the things that it connects to further downstream. In our case, if we think about this, we can think about this aggregation function, aggregating a weighted sum of the inputs as, in the logistic regression case, the calculation of a linear predictor, and then this nonlinear activation function as the function of this sigmoid activation. In neural networks today, in artificial neural network research, slightly different notation is typically used, and I'm going to now show that to you. So the more common notation is that we say that instead of a linear predictor, we call the output value often z, and that's a linear sum of the inputs x. And then the nonlinear activation function is simply denoted f, and its output is a, and that may be any one of a number of functions. In fact, neurons are not just acting alone, of course, but operating in ensembles. In fact, this is one of the key signature papers of the 20th century for the study of neuroscience. And this was simply a very simple sort of motivating idea, simply that we should ask, well, given these sort of input aggregating and output calculating properties of neurons, what happens when they're organized in ensembles? We wind up with circuits that can have interesting computational behavior. And so I'm now going to transition to our simplest initial neural network model of the semester. This is going to be a simple single hidden layer neural network. In this network, we're going to say there's an input layer, and for simplicity, we'll have only two varying outputs. Plus, now the yellow circles here are going to be what are called bias units, and they're always going to have the value 1. The green units are the input that's coming into the system, and they're going to be a varying value. So this is a 2-dimensional input. There are what are called hidden units in the intermediate layer. There are 2 hidden units whose values are computed as a function of the input, and then 1 hidden bias unit whose value is always 1, and then 2 output units, which are computed as a function of the hidden layer. And the prediction problem for this simple model is going to be a 2-class prediction problem. Is an output y based on the x is going to be falling into class 1 or into class 2. And the activation level of class 1, when this value is large, that's going to predict strongly class 1. When this value is large, it's going to strongly predict class 2. So all of these W's that I've annotated the neural network with are the weights of the connections. Those are those parameters. They're like the beta parameters of a logistic regression model, and they're the weights of a neural network model. All of the information contained in a neural network model is in its architecture, that is in the structure that you're seeing here, and in the weights. And this is a very complicated array of weights, and so I'm going to introduce you to some compact notation, similar to what you'll find more often in the neural networks literature. So we're going to take this first set of weights that connects the input layer to the hidden layer, and we're going to call that just capital W sub h, and we'll say that capital H, that is the entire hidden layer, is a function that is basically a matrix multiplication of the matrix of weights WH times matrix times the vector x, the input vector x. So we can summarize all those weights in that simple equation. We're now going to aggregate the hidden layer weights that is connecting to the output. In another equation, we're going to say the outputs, the eta outputs, are a linear function. They're a matrix multiplication of this weight matrix W eta, but it's not applied directly to H. Rather, first, remember, there is a nonlinear activation function that is applied to the hidden unit values. That nonlinear activation function is then going to be converted into outputs that they're then multiplied through by the weight matrix. So for example, this might be a sigmoid activation function. And so now we have this form. And the last part is to go from the etas to a prediction about whether y is class 1 or class 2. And we're going to do, once again, logistic, but in this case, we're going to call it something special. We're going to call it softmax output prediction. And that form is very similar to what we already saw for the logistic function. If this value were 1, it would be exactly the same as logistic. Remember, e to the eta over 1 plus e to the eta. But we're going to let both of these values vary. And that's sort of a way of practically allowing this approach to scale up to not only 2 classes, but potentially more than 2 classes. And so the softmax output prediction says that the probability of y being class 1, given the inputs, is e to the value of this node divided by e to that node's value plus e to this node's value. That's the denominator. And that's what's called the softmax output function, softmax prediction. So we might notate that as P of the set of y classes given a set of x inputs is softmax of eta, but eta, of course, is a function of the x's. What function is it? If we just put all these things together, then we wind up with P of y given x is equal to softmax of w eta times f of wh x, where f is this intermediate nonlinear activation function. Now, how do we do learning in this setting? We're going to do it once again with gradients, okay? So we have all these pieces, and gradient descent is basically saying, follow the gradient toward an improved version of what you're trying to do. So we define a cost function, which is, for example, this might be simply the likelihood of the data given the inputs and the model parameters. And to improve the model's weights from what they might be, we iteratively compute this gradient with respect to the weights, all the weights in the system, of this cost function. So the cost function is a measure of the discrepancy between whatever is predicted for y to be based on the etas and what y actually is. Now, you'll notice that the weights are sort of, and I'll just draw here a little bit to make it a little clearer. You'll notice that the weights are scattered throughout in this area and in this area. So notice that some of the weights sort of relatively directly connect to y, We just have to pass them through this, and we could re-express these etas as functions of these weights and functions of the h's. But some weights are in a much more indirect relationship with cost. So in order to actually compute, so remember that a partial derivative of a, that is d by d some weight of the cost, is going to implicate not only what's back here, we have to figure out, if I change this weight a little bit, well, what does it actually mean to, what does that actually mean in terms of manipulating this thing? And so this is the way that this is done. The crucial insight comes from the chain rule of calculus. And there's in particular a multivariate version of the chain rule. The chain rule in this case says that if y is a multivariate function of a bunch of u's, and u is a function of x, all the u's are a function of x, then if you, in order to calculate d by d, dy dx, you have to sum all of these products. For each of the u's that is a function, that f is a function of, you calculate dy by that du, and then you also have to include du, that du by dx. And then you sum all those together, and that's the gradient. Okay, so what does that mean in practice? That actually has important implications for how we're going to do learning in this setting. So let's start with looking at how we would calculate the partial derivatives. So this the partial derivative of the cost with respect to this weight is relatively straightforward to calculate. We just hold the rest of the system constant. I'm not going to show you all the math, but the math is pretty simple to do here. And we can do this likewise for all of these gradients connecting the hidden layer to the output layer. Okay, so that is relatively straightforward. What's less straightforward is when we want to calculate the value of the partial derivative with respect of cost with respect to a weight back here. Because of the chain rule, we'll see that, well, this weight only influences y through these two weights. So we actually have to consult, first of all, we have to use the chain rule to rewrite this as the product of the sum of these two products of partial derivatives. Now, notice that each of these contains something that we've reused before. This part was here, okay? And this is the partial derivative with respect to this weight of the cost. And then the chain rule says that that should be multiplied by the partial derivative of this weight's value, which will be determined by this hidden node with respect to this derivative. And then likewise, we have to do it again with the second case, with this case. And that is, now notice that this is stuff that we've already computed. And so if we've stored these values the first time we computed them, we can reuse them when we populate the partial derivatives over here. That idea of storing and partial derivative values is the notion of backpropagation. And this is an instance of dynamic programming. Now, there's technical details that I'm not getting into here. In fact, what's stored is not the partial derivatives themselves for weights, but the partial derivative for node values. And then those can be reused. But this is the basic idea of backpropagation. There's more to say about the details of how to implement backpropagation. I'm not going to get into it in this course, but there are lots of resources, and I'm going to provide those to you later. Okay, so let's go back to our XOR example and just see what happens. So I've reproduced this simple two-layer hidden neural network with two inputs and a two-unit hidden layer plus a bias layer, so plus a bias unit at each of the input and the hidden layer. We will initialize the weights randomly. And what I've plotted out for you here is that as a function of x1 and x2, for inputs of values 0 and 1 for each of x1 and x2. So we have two different classes, the red class and the yellow class. This is the decision boundary. None of it is close to 0.5. It's just a random. This is just sort of a contour plot of equal probability of class A lines. But what I'm going to show you is that as we train the model by exposing it in epochs to data from the 4 data points, and in each epoch we collect the gradient, we accumulate the gradient over those 4 data points, and then once we've got that accumulated gradient, which is just the sum of the gradients of each of the individual data points, we then move the weight a bit, and that a bit is what's often known as learning rate, in the direction of the gradient. And I'm going to show you with a very low learning rate what happens here over hundreds and actually a couple of thousand epochs. So you can see early on, it's still linear, but now actually the decision boundary, it started classifying this point, and now it's turned into something nonlinear, where it classifies at the end after 2,000 epochs. The 2 points here and here are in a region of high probability of class B, and these are in a low probability of class B. Okay, so it's actually succeeded over training of multiple epochs. So from random initialization, this model can and does learn to represent a nonlinear decision boundary for the XOR problem. And in fact, this is a simple case of a much more general thing that's known, which is that as just having one hidden layer in a neural network makes a neural network a universal function approximator. That is, any function can be that you want of the inputs can be approximated to with some sort of sanity, sort of mathematical behavedness constraints on the function. Any such function can be approximated as close as you want if you have a big enough intermediate layer. So maybe it's a weird shape, high order polynomial type thing. Maybe in 2 dimensions, it's a weird decision boundary. You can get as close as you want to it with a single hidden layer in your network. That is, it can be represented. Now, whether it can be learned is often a challenge. Okay, so that's the ability of neural networks with at least one hidden layer to represent nonlinear classification problems, which is incredibly powerful and really is the fundamental source of the explosion of success in deep learning throughout the last decade and beyond. One other minor note I want to make before taking a break, which is that we won't always be using the same activation function, the sigmoid activation function, for the intermediate layers. At the end, there are good reasons to use the softmax function because it transforms the activation levels into probabilities over a multinomial set of class outcomes. But the intermediate layer activation functions, there are good reasons to choose something different. And the fundamental reason is that the sigmoid as a nonlinear activation function, once you get deeper layers, which turns out to be very powerful and effective, you often wind up using other functions because the sigmoid function has very small derivatives at the tail. Okay, so once you have relatively large weights, it can become very difficult for the network to detect any sensitivity to changing the weights. That is, like, you'd have to change the weights a massive amount, and it seems like that it's very difficult to predict, to actually estimate exactly how much would be good to change, and that becomes very difficult once you get more and more layers, because these small derivatives multiply back through. You saw that in the backpropagation example, many derivatives are getting multiplied through with each other as you go farther and farther back from the output. As a result, other functions for H, for the nonlinear activation function H, have become more popular. Here, in addition to sigmoid, here are some other ones that are often used. I want to draw your attention especially to the ReLU and the leaky ReLU, which are actually linear at levels greater than 0 and either flat at 0 or just almost flat at less than 0. And those actually turn out to be much better for deeper models. So we'll now I'll take a break, and then I'll be back with you in just a second to look at applications to language.